Previously, we've dealt with what are known as discrete random variables. These are variables that take on only a finite or countable number of values. Examples of discrete variables would be the number of defective clocks in a sample, the number of students who say they like math, houses in a neighborhood, things like that. Continuous random variables would be numbers such as the heights of people, the lifetimes of light bulbs, the length of phone calls. For example, if you're looking at the height of people, we are not limited to exactly 5 feet 1 inch, 5 feet 2 inch, 5 feet 3 inch. We can go anywhere in between. Anything along a continuum is a possibility. That's why we call it a continuous random variable. For many continuous random variables, most of the data points fall near the center and there are fewer near the end. Distributions like these resemble what we call a normal distribution, which is a very particular type of continuous random distribution. Its graph is called a normal curve, or sometimes a bell curve because it is bell-shaped. These are examples of normal curves. Notice all of them are higher in the middle and they get closer to the x-axis as we go out to near the ends. This tall, narrow one is one that's not very spread out. If a graph is not very spread out, if our data points are clustered near the center, we say that we have a small standard deviation. You should be familiar with that idea. If there are more data values toward the ends and fewer in the middle, then we have a larger standard deviation. In this one, this broader, flatter curve, we still have more near the middle than we do anywhere else, but we certainly have more that are further out toward the ends than we do with the tall, narrow one. So the standard deviation for this curve is larger than for either of the two others. The normal distribution is the most important distribution in mathematics, science, social science, and other fields. It turns out that many other distributions, including discrete distributions such as the binomial, can be approximated by a normal curve, and that turns out to be very, very useful. Here are some properties of the normal curve. It's bell-shaped and symmetric around a vertical line. The mean is at the axis of symmetry, so right in the middle. The shape is completely determined by the mean and the standard deviation. Once again, a small standard deviation means it'll be tall and narrow. Large standard deviations means it will be more spread out, and so flatter and broader. The area between the curve and the horizontal axis is always 1. If you recall, in any probability distribution, the total of all the probabilities has to be 1. For continuous, we cannot just total them individually in the usual way of totaling, but it does turn out that there's a comparable idea to totaling that has to do with area under the curve. It requires calculus to do it, but it turns out that the area under the curve in all of these is 1. Regardless of the shape, that means the mean and the standard deviation can differ. We're going to have 68.3% of the area within 1 standard deviation of the mean, 95% of the area within 2 standard deviations, and 99.7%, that means nearly all of it, is within 3 standard deviations from the mean. So if you have a data point that is more than 3 standard deviations away from the mean, then that's what we call an outlier. It is very, very much a non-typical value. It turns out areas under the curve, which will correspond to probabilities, can all be determined using only one table, regardless of our mean and our standard deviation. And we will learn how to do that. The way we're going to do it is by looking at something called the standard normal curve. This is the normal curve that has a mean of 0 and a standard deviation of 1. Other normal curves are related in the standard normal in this way. On our regular curve, our non-standard curve, we'll go from mu to mu plus z sigma. Under our standard normal, we'll go from 0 to z. Our z is what we call a z-scores, and that tells us how many standard deviations a value is away from the mean. If we look at mu plus z sigma, if we have some x value, and let's say it's a certain number of standard deviations away. So we're going to start with the standard deviation. We're going to add a certain amount. Back up. We're going to start with the mean, mu, and then we're going to add a certain number of standard deviations. Z tells us the number of standard deviations. So we're going to take our mean mu and add z sigma. Let's solve this for z. So what I'll do is I'll do x minus mu is equal to z sigma. And now I will divide both sides by sigma to isolate the z. And so now we end up with z equal to x minus mu over sigma. Get used to this formula. We'll be using it a lot. Let me write that a little bit neater. So it turns out that if we're in the standard normal curve, we'll be looking at the z-score for A and the z-score for B. If we're in our whatever other normal curve, we'll be looking at the area between A and B. And those two areas will be identical. And we're going to be able to look them up all on one table. Let's do an example. Let's suppose we have a normal distribution with a mean of 10 and a standard deviation of 3. And we want to find the z-score corresponding to 28 and to 7. So for 28, I'll call this z28. It's going to be x minus mu over sigma. So we're going to do 28 minus our mu. Okay, so our mean of 10, that means our mu is 10, and our sigma is 3. That's our standard deviation. So we do 28 minus 10 divided by 3, which is 18, over 3, which is 6. What that tells me is that an x value of 28 is 6 standard deviations above the mean. Okay, let's think about that. So 6 standard deviations above the mean. So that means I would do mu plus 6 sigma. My mean was 10. My standard deviation is 3. So if I add 6 times 3, that gives me 10 plus 18, so 28. Now we want to find the z-score corresponding to x equals 7. Well, just think about it. Ask yourself, how many standard deviations away from the mean is the value of 7? Well, one standard deviation would be 3, so if I go 3 below the mean, that would put me at 7. So an x value of 7 is 1 standard deviation below our mean. That means my z will be -1. Let's check this by looking at our formula. Okay, my z for my x value of 7 will be x minus mu over sigma. So that'll be 7 minus 10 over 3, which will be negative 3 over 3, so negative 1. So we could figure out with the formula, and that's fine, but it's also good to notice and to comprehend that the z-score is nothing but the number of standard deviations away from the mean. If the z-score is negative, that means our data point is below the mean. If our z-score is positive, our data point is above the mean. So here we're 1 standard deviation below. In the first example, we're 6 standard deviations above the mean. The z-score is the number of standard deviations between the data point and the mean. To determine areas under the curve, and thus probabilities, we'll use a table. You have one in your textbook. The probabilities of x falling inside a certain range of values are given by the area under the normal curve for that range. Remember, values of x correspond to z-scores on the standard normal curve. So let's suppose that we have a normal curve with a mean of 7 and a standard deviation of 2. That means our mu is 7 and our sigma is 2. We want to determine the area under the curve between 7 and 10. So let's draw a sketch which shows the area that we are trying to find. My mu is 7. Remember, your mean will be in the middle at the axis of symmetry, which will be at the highest part of your graph, and because 10 is larger, that'll be to the right. So this shaded area is the area that we want to find. Areas of this shape are listed in our textbook by the corresponding z-score. So we need to find the z-score that corresponds to 10. So according to our formula, we do x minus mu divided by sigma. So that'll be 10 minus 7 divided by 2, which will be 3 halves, which will be 1.5. And so that tells me that we are 1.5 standard deviations above the mean. Let's see if that makes sense. Let's look at our standard deviations, 2 units. That means if we were 1 standard deviation above the mean, we would be at 7 plus 2, which is 9. Onto that, add half a standard deviation, which would be 1. Half a standard deviation onto the 9 would put me at 10. So therefore, if I start at 7 and I add 1 standard deviation and half a standard deviation for a total of 1.5 standard deviations, I will be at 10. They don't always, our z-scores do not always work out to be integers or halves of standard deviations like this. It's not always just 1 or 1.5 or 2 or 2.5. But make sure that you remember that when you calculate the z-score, that number actually means something. That means the number of standard deviations above the mean. So what we do is we look up that z-score in your table. So we look up z equals 1.5 in your table, whatever table you are using. It should give you an area of 0.4332. That's the area that we are trying to find. Now, this area corresponds to a probability. The probability that the variable is in between 7 and 10. So let's let x represent our normally distributed variable. So it's in between 7 and 10. So we're trying to find the probability that x is in between 7 and 10. This corresponds to the probability that z is in between 1.5 standard deviations above the mean and 0 standard deviations above the mean. What does a z of 0 mean? That means I'm exactly right on the mean, which is 7. So this is going to be equal to that same area, 0.4332. Every time we find an area under the normal curve, we are finding a corresponding probability. Let's use the same example, but let's move on. Let's find the probability that the variable is in between 6.5 and 9.7, and recall that our mean was 7 and our standard deviation was 2 for this example. So once again, let's draw a sketch that depicts the area that we want to find. So here's my standard normal curve. My mean of 7 is right in the middle. I want to go from 6.5, which is just slightly below the mean, to 9.7, which is above the mean. So this is the area that I want. However, areas of this shape do not appear in our table. In our table, all we have are areas that are from our mean to our x value. So what we need to do is break this up into areas that look like the ones in our table. So we're going to break these into two pieces. In the first, we'll go from 6.5 to 7. So that'll be this area. And then if we add to that the area from our mu of 7 to, let me change this a little bit and draw it a little better. We're going to go out from our mean of 7 out to 9.7. So now we've got an area that looks like this. So if we can find each of these areas, then we'll add them together to get the area that we want. I'll call these A1 and A2, just so that we can call them something and have clear notation when we're referring to our areas. So first of all, we find the z that corresponds to an x value of 6.5. So we do 6.5 minus 7 all over 2, and so this gives me negative 0.25. That means I'm 1/4 of a standard deviation below the mean. Now, if you look in your table, you do not find areas corresponding to negative z values. That's because they are not needed. The area that falls under the curve from 1/4 below the mean to the mean will be exactly the same as from the mean to 1/4 above. In other words, from symmetry, we're going to have exactly the same area that we would have that corresponds to z equals positive 0.25. So while we do know we're below the mean, we're going to ignore that negative sign temporarily. We're going to look up z equals positive 0.25 in our table. From a symmetry, we're going to have exactly the same number for each of these two z values, so there's no need to list them both in the table. So here my area in my table turns out to be 0.0987. Now let's look up, first, actually before we look up, let's calculate the z-score for 9.7. So we do 9.7 minus 7 all over 2, and that gives me a z-score of 1.35. And so then we look up 1.35 in the table. When you do, you should get an area of 0.4115. So now we have the two areas that we need. We just need to combine them to get our probability. So our probability that x is in between 6.5 and 9.7, that's exactly the same as the probability that my z-score is in between negative 0.25 and positive 1.35. So So we look at our sketch that shows us how to combine our areas. We know we're going to just be able to add these to get the shaded area that we want. So we do A1 plus A2, 0.0987 plus 0.4115. Add those together and you get 0.5102. So just over 50% of the area falls in that range. As usual, remember your probability will always be a number between 0 and 1. Let's do another one. Let's figure out the probability that our variable is less than 4.52. Once again, we're working with our normal distribution with a mean of 7 and a sigma of 2. So we draw our sketch. Don't skip drawing the sketch. It really helps you to combine the areas in the correct way because there are several different possible things that can happen. So we have a mu of 7. 4.52 will be to the left. You want to make sure that your x values are on the correct side of your mean. So that's the area that I want. Once again, I do not have areas of that shape in my table. So I need to figure out a way to do it. Here's what I'm going to do. I remember that my normal distribution is symmetric. That means, whoops, I shaded the wrong half. Sorry. If I took the left half of this, everything below the mean, how much will that be? Well, the total area under the curve is 1, so this will be 0.5. So if I do that, remember my 4.52 falls in between here somewhere. So now, the area that I can look up on the table, I can look up areas that look like this. So how do I combine these to get the area that I want? Well, if you just take this half, the 0.5, and you subtract, that shaded area will have it. I'm going to call this shaded area I guess we'll call it A3. We already used A1 and A2, whatever you call it. Okay, that tells us what our plan is. So now we need to find the z-score that corresponds to 4.52. So we do 4.52 minus 7 all over sigma, which is 2. That gives me a negative 1.24. We expect it to be negative because we're to the left of the mean. And then we're going to look up z equals positive 1.24 in our table. From symmetry, we can look up the positive instead of the negative. And so what that gives me is an area of 0.3925. Now, how do I find the area that I want? Well, I know I want the probability that x is less than 4.52. That's going to be the same as the probability that z is less than negative 1.24. This will be 0.5 minus A3 so 0.5 minus 0.3925. That gives me 0.1075. That's the probability that my variable falls below 4.52.